topic of my presentation is control of spectrally crowded systems. So I'll start by discussing what ways we have to create entanglement, and specifically how you need to couple qubits together and the different paradigms which exist in order to mediate entanglement between qubits. So the first one, and this is a sort of a generic list, pretty much every qubit can be put in one of these categories. So the first way is to have some qubit states that are part of the Hilbert space, and then identify some states outside your qubit subspace, so additional auxiliary levels in the Hilbert space, and use those because they have some property of being delocalized over the Hilbert space to mediate interactions between two different qubits. So a canonical example of this would be atomic systems, for example, trapped ions, where people optically excite the qubits to these optically excited states. These states talk to other qubits, the analogous states of other qubits, through essentially phononic modes, vibrational modes. And that way an interaction is switched on optically and then switched off when you bring your system back to the Hilbert space where the qubit lives. So this is one way, and other atomic systems, of course, belong here. Another way is to just tune your energy levels. So now we're staying within the Hilbert space of the qubit, and we're in a regime, in the idle regime, where the qubits don't talk to each other. So you can think of detuned qubits so that the interactions are suppressed. And then you go to, you have some parameter. In this example of quantum dots, it would be the exchange interaction, which you tune, and you go to a regime where the two qubits talk to each other strongly. When they talk to each other strongly, a canonical gate would be an exchange gate or square root of swap gate. Something similar can be done for superconducting qubits where you allow to tune some voltage or some kind of flux. And again, you bring your qubits into resonance, let them talk to each other, accumulate whatever entangling gate you want, and then tune them back to your idle point. And a third paradigm is do nothing of the sort. Just have your qubits sit in the same parameter regime at all times, so that your interactions now are always on. You definitely need interactions, obviously, to mediate entanglement. So in this case, you need to live with a system where you don't have a tunability, you don't have the ability to go to other parts of the Hilbert space, or you don't use this ability, and you need to somehow create single and two qubit gates in that system. So you might wonder what are the relative merits, advantages, and disadvantages. So in this case, in the idle state, the qubits are typically very well isolated. They're not coupled at all, and they're typically also not coupled strongly to the environment. However, when you go to these excited states, they tend to be lossy. In this example, they're optically excited states. You have a spontaneous emission, and anytime you leave your Hilbert space, you run the risk of leakage. So those are the issues with this. In the case now of tuning, the advantage is again that the qubits retain their single qubit character when you're away from this anti-crossing point. But the disadvantage is that anytime you start tuning things, and you have voltages and so on, you can induce charge noise, which is a very prevalent issue both in superconducting qubits and in quantum dots. And finally, in this paradigm, your system, the advantage is that your system remains at the sweet spot, which is famously the advantage of a transmon qubit, and the reason you don't want to tune these things. However, you have to deal with this issue that sometimes is maybe not very well appreciated outside this community, which is that you have couplings that are always on, and you have to design your single qubit gates and your two qubit gates simultaneously in this always coupled system. And that's going to be largely my focus today. All right, so a lot of the techniques I'll talk about are general. They apply to systems that look like this, but a lot of them can be also extended to tuning systems and to this case. But for concreteness, and because our interest was a lot experimental concerns in superconducting qubits, I'm going to focus on superconducting qubits and specifically with the transmon in mind. So when I was preparing this talk, I was anticipating that Leo would be before me, so I didn't want to burden you with repeating too much about the system. But all we need is in this slide and in the few next slides anyway. So this audience must have seen slides like this many times. You can think of a superconducting qubit as originating from a circuit, superconducting circuit. In that case, of course, you would have a simple harmonic oscillator. You cannot control, you cannot make a two-level system out of a simple harmonic oscillator, because if I drive here, I'm going to start driving everywhere. And for that reason, you want to put some nonlinear element in here, which is the Josephson junction. So that's exactly what creates an unharmonic oscillator out of your harmonic oscillator. And moreover, in the case of the transmon, people choose the unharmonicity to be very weak, which brings us in a regime where the charge noise is low. So the flip side of that is that we have to live with a very unharmonic, with a very weakly unharmonic oscillator, which means that we're close to this, which suffers from leakage. Moreover, the states here are approximately equidistant, the transitions. So if you look at what the spectrum looks like, so here I just took two transmon qubits coupled by a cavity, this resonator shown from this image from IBM. And all I'm doing here is I'm just plotting the spectrum. You see that it looks terribly messy, right? So you have some ground state that's pretty clean, then you have a few excited states, and then you get denser and denser. So anytime I want to implement some gate, I need to go here and drive one or more transitions, and I need to avoid all the other transitions in the system, which would, if I drove them, they would just cause me error. So this is a generic problem, and I'm sure this community appreciates this very well. There's this inherent competition in terms of how fast I can control a quantum system. And the competition comes from, on the one side, the time energy uncertainty principle. So if I have a pulse that has some duration, delta tau, then if I make this pulse very fast, I'm going to start exciting off-resonantly transitions that are within this 1 over delta tau from the transition I was going for. So the answer to, if this were the only problem, the obvious answer would be just make your pulses extremely long, and then you can just spectrally select and you're done. However, we all know we have this problem of finite T2, so your superposition decays into a density matrix, and that sets an upper limit on the duration of the pulse. So you have to live in any type of control, you have to live in this, whatever the system allows you based on these two constraints. And this is the more severe one, right? This one is a coherent error, and you can do hopefully a little bit more with it. So that's going to be a lot of my focus. All right. So now the first question we need to address is how do we implement two-qubit gates in the system where I'm not allowing myself tuning, and I'm not allowing myself to be in a nice regime where I switch off interactions and I switch them on at will. And people have, of course, thought about this problem for a while and have come up with various solutions. This is not an exhaustive list of what people have proposed and tried, but it's a pretty characteristic list in this community. So the most famous, arguably, gate in the all-microwave control of superconducting qubits is a cross-resonance gate. And this has been developed over the last more than 10 years. So here what happens is you have two qubits you want to entangle, and you drive the one qubit at the resonance frequency of the other qubit. And in that way, in some rotating frame, you create some effective interaction that is amplified by this drive. And then when you switch off the drive, this interaction is switched off. And if you look at the earlier implementation of this gate, this takes 200 to 300 nanoseconds if you don't do much more to it. And the fidelity initially was not very good. IBM has worked very hard on improving this gate. So more recently, they've managed to go below the 200 nanosecond time and to push their fidelities very high. This had to be assisted with many different pulses, decoupling interactions, and so on. So this is a very non-trivial thing to achieve. And it's not obvious that if you achieve it for a pair of qubits, that it immediately translates to another pair. There's other gates, this map gate, where people have allowed themselves to exit the qubit subspace. You still have this issue of always-on interactions, and something else called the ERP gate. I'm not going to insist on these too much, but you see here characteristic timescales. For typical parameters of your device, you are in the several hundreds of nanosecond regime, and the fidelities are roughly average on the order of 90% or so. So since the cross-resonance gate is the most common one, and it's what IBM is pushing further, I just want to point out here sort of an inherent issue with this gate. So one requirement for this gate is that, for this gate to perform well, is that the coupling needs to be smaller than the difference in frequency of the two qubits, but at the same time, the frequency difference of the two qubits has to be small compared to the non-harmonicity. So you again live in this very narrow window where your gate works well. And it's this list and the fact that it doesn't, if you look throughout these gates, they don't perform as well as we would like in order to do some non-trivial quantum computation that motivated us to think, can we do better? So this takes me to our work, and sort of first I wanted to just give you a flavor of what our approach is before I start bombarding you with details. So what we do is we want to have some sort of analytical component in our work, and I'm going to justify why I want to do that. But to have that, you need to start from some effective Hamiltonian. You can't just take this huge Hilbert space and hope to solve things analytically. So you have to start from some effective Hamiltonian, which has to be chosen well enough that it's sensible that a lot of the errors, the intricacies are in there, and whatever controls you design are already taking into account these caveats. So hopefully, starting from some effective Hamiltonian, I'm going to show you in detail what I mean. Then you come up with some analytical pole shaping. And of course, you have to deal with the fact that your Hilbert space is not the simplified thing you started off with, but contains many levels, many transitions are allowed, and so on. In principle, if you start with the unharmonic oscillator model, this is an infinite Hilbert space. When I say here we do simulations in the full Hilbert space, we obviously truncate this Hilbert space, but we do it in a way that we make sure our results have converged. So wherever we stop, including levels, we have checked that our fidelities and so on don't change. Okay, and then once we do that, of course, the gate doesn't perform as well as you would expect starting from your effective Hamiltonian, so you do need to do something numerical here and improve it. You can do one of two things. If your fidelities are already pretty good, all you need to do is just tweak some parameters, and you quickly get something much better. And the other thing you can do is use whatever you did here as an initial guess for optimal control theory. And we have done both, and I'll show you results for that. So why do we want to do this messy thing if you can just start with numerics right away? So the case for doing something analytical is the following. The first is that it's general. If you decide to change the frequency of one of the qubits by a little bit, and I have already designed the pulse numerically, then that pulse won't perform well anymore. If my technique is analytical, then all I need is to go into my equations and change some parameter to account for the change you did. So that's one reason. The other reason is that the techniques then are more general and transferable to other physical systems. And then there's also the practical consideration that oftentimes, if you don't start with a good guess in optimal control theory, you can get stuck in local minima, and we've seen that. Whereas if you start from something that already performs well because you optimized it analytically, then your OCT algorithm will give you something very good. All right. So now let's think about how these ideas are, let me show you how these ideas are implemented for 2 qubits coupled by a cavity. And I'm going to talk about larger systems as well. So I told you that we start from some effective Hamiltonian. And the question is, what is this effective Hamiltonian and what Hilbert space does it live in? So if I look at typical spectra in the case of two transmon qubits coupled by a resonator, and I ask what are the transition frequencies, then you will notice that they look something like this. So I have some transition where I want to drive 1 qubit conditional on the state of another qubit, right? So that would be my starting point for doing an entangling gate. But then I have a nearby transition, and this nearby transition is not hard to understand what it is. All it is the same transition for my target qubit, but I've changed what the control qubit is, what state the control qubit is in. So, and then these other transitions correspond to all the other transitions in the system. So higher excited states, or putting 1 qubit in the state 2, and so on. So the reason, it's not surprising that my spectrum looks like this, because I'm in a relatively weakly coupled regime. I want my qubits to retain their single qubit character, right? And if they absolutely retained it and I had no interactions, these two transitions would just fall on top of each other. Okay, so now what do I want to do given this spectrum? So what you would think naively is you go and you drive this target transition and you avoid everything else, right? Let's say you want to do a CZ gate, then you just have one transition, you want to implement this minus sign, and everything else has to be avoided. What we decided to do is, in order to speed up our pulses, to go and take the nearest competing transition and incorporate it into our dynamics. If you do that just by a very rough order of magnitude estimate here, what you're avoiding now is no longer this red transition, these are the black transition. So now your pulse, in principle, can be sped up by an order that's given by the ratio of this delta over this epsilon, right? Because you're no longer avoiding the red guy. So if you look at a cartoon view, this is what we want to do. We want to go here and do the prescribed gate in one of these two subspaces, and we want to simultaneously allow our pulse to drive the other subspace, but in a way that it acquires a trivial phase. So to emphasize this point, instead of 1, I made this e to the 2i pi to show that this transition has undergone some dynamics. And we call this Swift, following the tradition of people giving names to pulses and pulse sequences and so on. Okay, so this is an idea, but of course now the difficulty is how do you implement this idea? And before I tell you that, let's first look a little bit more closely at what our qubit states are and what our Hamiltonian looks like within this 4x4 Hilbert space, right? I'm going to talk about the rest of the Hilbert space later numerically. So because my interactions are always on, now I need to look at the dressed states. So I take the interactions into account, I diagonalize the total static Hamiltonian, and now I need to define my qubit states, right, as being the states that I would have in the absence of the interactions. And here, the third index is the cavity. So I'm assuming I'm trying not to populate the cavity. But I also have these extra states here that hopefully are only a small contribution because there's these always-on interactions. So my qubit states now have been redefined. So then, in this basis, in this new basis, my drive Hamiltonian, I'm ignoring the static part now, looks like this. I have, so here I'm assuming I'm only driving qubit number 2, right? So here I have qubit 1 is in state 0, qubit 1 is in state 1. So if I drive qubit 2 in an undressed basis, this is all you would have, right, clearly. But in my case, I also have some residual terms coming from the fact that I have these states being part of my dressed basis. And one thing we found is, so one thing we're assuming to begin with is that this part can be ignored. Ideally, eta here is much, much smaller than c, so that's not a bad approximation. Of course, it's an approximation we're going to check numerically. So then the Hilbert space that I'm left to work with, and the form of the drive Hamiltonian is this block diagonal form. And this block diagonal form I can hope to live with, and I'll show you what we do. So now, given this block diagonal form, which I put now in some rotating frame, this is what I want, my objective. I have these two subspaces. I want one of these subspaces to be driven in a trivial fashion, so to just perform an identity. And I want this subspace to be driven as non-trivially as possible, namely to obtain something that's locally equivalent to a C0 or a CZ. So this I want it to be a pi pulse, a pi gate in some basis. So now the question is, how do you do that, right? So you have these two blocks. They have the same pulse. What they differ by is how resonant your pulse is with each of them. And I want to have the same pulse and analytically extract what are the dynamics in each of these two blocks. And we follow two ways of doing this. We need to worry about analytical solutions of the time-dependent Schrödinger equation. And we need to worry about them in a 2x2 case because thankfully we can deal with two decoupled blocks. So one approach you can think of is just find whatever analytical solutions already exist and use those and hope this will work. Second approach is find new analytical solutions, and we've done both of these. So let's start with approach number one. If you ask what are the analytical solutions that are known in the literature, you can quickly see that you make a very short list. This might not be fully exhaustive, but these are typical analytically solvable pulses known in the literature. So the square pulse is the most well-known example, is what you solve to get Rabi oscillations. We've heard in other talks people discuss why square pulses are not always ideal. They can be distorted. You don't always have, you don't have the infinite rise time that you need. So we don't want to use the square pulses. There's other analytical solutions here. And the well-known one is the hyperbolic secant, which has this shape. And I'll show you why we want to start with this one. So this was first realized by Rosen and Zener back in a physical review paper in 1932, that in a two-level system, you can solve the time-dependent Schrödinger equation for a hyperbolic secant pulse analytically. So it's a long time ago. And then in the 70s, this pulse was somewhat resurrected because of self-induced transparency, if that's familiar. Okay, but it's aside from being analytically solvable, this such pulse has another nice property. To demonstrate this, I've plotted here something that looks like Rabi oscillations, but because I have a shaped pulse, I don't want to change, unlike the square pulse where you just let it go. Here, what I'm doing is I'm just changing the strength of the pulse in the x-axis. Okay, so that's why I put Rabi oscillations in quotes. So if you do that, and you see and you compare how does the square pulse behave, how does a Gaussian pulse behave, and how does a such pulse behave, you see strong qualitative differences going from left to right. So in the case of a square pulse, the period here changes a lot. Oh, and I should say that the different colors are different detunings. So as I change the detuning, I get a return at very different strengths of the field. If I go to a Gaussian, I get something that looks a little bit more canonical, so I'll change the tunings. But again, I have these shifts here. If you look at the hyperbolic secant, you see that this blue curve here is a resonant case, right? So this condition here is the 2-pi pulse. And you see that as I change the tuning, the 2-pi pulse retains its 2-pi pulse character. I return to the ground state irrespective of what my detuning is. And this is a very property, and it has somehow to do with the non-adiabaticity. If you look at adiabatic pulses, you don't have this property. So the faster you make a pulse, the closer it goes to this. But for this case, for the case of the hyperbolic secant, it doesn't have to be fast. This is an exact solution. The only approximation here is rotating wave approximation. All right, so now why is this property interesting for us? The one reason it's interesting is that if I want to do entangling gates, one of the simplest things you can think of is controlled phase gates, right, CZ gate. And in CZ gate, what I want is I want to acquire phase, right? I go cyclically to some excited state, I come back, and I pick up this -1. So, but here, right, and of course that's a well-known property for resonant pulses. If I go from a state up to an excited state and come back resonantly, I always pick up this -1, which is also familiar from SU2, right, from the spin. And that's what we know from the Rabi oscillations. Now, in the case of the Sech, I can allow myself a detuning, and then I can ask myself, since everything is analytically solvable, what is the phase that my state picked up under the cyclic evolution that's now in a detuned system? And in the case of a 2-pi Sech, the analytical expression comes out to be this. But you can also look at 4-pi and stronger pulses, and then you have some more complicated expressions. The interesting thing from our point of view, if you go back and think what our objective was, is that now I have a pulse that I can make it be transitionless in 2 subspaces. So if you take this expression for the phase, in the case of the 4-pi, and you plot the phase as function of the detuning, and here I have the detuning in units of bandwidth, here's what you see. The obvious thing is that if I have a 4-pi pulse and I go resonantly, so I go twice around the Bloch sphere, I pick up a plus sign, right? This is the famous result from spin where you need to do this double rotation to go back to yourself. Fine, so this is well known. This is not surprising, right? I pick up a 2-pi. But now if I detune, I can pick some detuning where my transition acquires a -1, and that -1 is, of course, exactly what you want for a CZ gate. So why are we interested in this? I have these two blocks, right? I have these 2 simultaneous transitions I want to drive. So I can arrange things so that one of them is resonant. If one of them is resonant, then I pick up a trivial phase, +1, and that guy is driven, but it's not messing up my dynamics. And then I still have a knob here. The detuning between the transitions is fixed by the system, but I have this bandwidth knob. So now I can change my bandwidth so that the other transition acquires a -1. So that's the reason that this pulse shape is so ideal for this scenario, and we looked at that in the case of transmons where we went outside the Hilbert space to acquire these phases. So now you can also notice, this is what I discussed now. Another thing you can notice is that if you again look at the phase as a function of the detuning, there's more than one transitions that satisfy this trivial phase requirement. So you can, if your spectrum allows it, you can drive even more transitions. And you can have something similar for the 2-pi pulse. I'm not going to go into too many details here. You need to also have some local unitary gates. OK, so this is the design. I simplified my problem a lot. I picked a 4x4 Hilbert space out of this mess of states. So now a reasonable question is, how well does your pulse really perform? And to do that, we went back to the full spectrum. These states are really dressed states. The first index here is the cavity. The other are the qubits. And in the design I just showed you, this was my target transition, and this is my harmful. You can't quite tell here because there seem to be many transitions that are competing, but this is the closest one. So now what we want to do, what we did is do simulations and see how well our pulse performs in a realistic system. So here are just some typical parameters. We did not fine-tune the static parameters here at all. We just picked something that's reasonable. And here what I'm plotting is the diagonal elements of the evolution operator. as a function of time, right? So this just shows you how the time dynamics progress. And I'm restricting myself to the qubit subspace. So you see, I have the two transitions that are strongly driven, one that's connected to state 0, 1, and one that's connected to state 1, 1. And here you see that I have the cyclic evolution, right? I go to this drops and goes up, and here I go to -1, just like I wanted. And if you look now at what happens to the absolute value of the same matrix element, you see that I have this 2 peaks, which indicates this 4 pi pulse, right? My population dips twice and goes back. All right, so this fidelity, this is of course simulation, so it's in some sense it's not fair to compare to experiment like Henri mentioned yesterday, but in principle you see you can get pretty comfortably a few 9s without having optimized too much. And the time scale already comes out to be 160 nanoseconds, which is much less, and it's something we expected up front, right? It's not surprising because that's why we designed our pulse this way. Now you can do better. You can also optimize numerically. So here I'm plotting bandwidth, which means that faster pulses are to the right. So you expect that the faster your pulse, the more states transitions you couple to, the worse you do. And the fidelity should be dropping as you go to the right. So now I can take a 2 pi pulse, and I call this naive, meaning that I'm trying to avoid every transition, including the one that we didn't incorporate into our dynamics. And there, of course, you see that you do very badly because you're quickly coupling to this transition that is incorporated here. Whereas if you do either a 4 pi or a 2 pi pulse, your fidelities are much better. This is what comes out of our analytical solution. You see that numerics help you a lot. They push the infidelities by a few orders of magnitude. And this is not too sophisticated. This was just tweaking parameters a little bit. Okay, so this was the results for SETCH. I'm going to talk about experiment near the end of the talk. So now you can ask, is that the best I can do in terms of speed, right? 160 nanoseconds at the time we published this was about half of what people were getting. But now, you know, it's reasonable to ask, can I do even better? Is there some inherent limit here? So what can we improve? One is we can tweak system parameters. This is an important point. It's a little bit boring, right? But I'll go back to it. You can use a subspace where the shifts are stronger. You're ultimately limited by the fact that the cavity, right, you're in this trade-off between being coupled enough to have strong 2-qubit gates and weakly coupled so that qubits remain individual qubits. One issue in superconducting qubits is that the cavity, for coherence reasons, is chosen to be at higher frequency than your qubits. As a result, and because as you go up the ladder, you become more enharmonic, smaller transition frequencies, then in the ground state, in the Hilbert's qubit subspace, you have more couplings. And the third thing is explore other solutions beyond the SETCH. The SETCH was just given to us by Rosen and Zener. It was very convenient, but it's not necessarily the best we can do. So to do that, we looked into techniques developed by my colleague Ed Barnes, who's here at the conference as well, of new solutions to the time-dependent Schrödinger equation. So the typical paradigm is, of course, you start from the Schrödinger equation for the evolution operator. You have some Hamiltonian, someone gave you this pulse, or you just came up with it. And the standard strategy that people have been using for years is try to find an omega of t that gives you a solvable differential equation here. And what was developed in these papers was an alternative strategy. So instead of instead of treating this as an equation for u, treat it as an equation for the pulse. And then d is related to the evolution operator. Then you can solve this analytically. This has a solution. So then what you would need is to come up with different evolution operators And all you would need is to essentially differentiate them. You don't need anything harder. And you come up with new pulses. So, of course, you need to impose physical constraints. One is that you need your evolution to be unitary. But you can build that into the formalism. So this is what Ed did in these works. So the trick was to parameterize the evolution operator in terms of a new auxiliary function called chi in this formalism. So sometimes we refer to this as the chi formalism. And then you can solve for both u and the driving field as a function of chi. And you see here, from requiring this to be real, you have a constraint in terms of the derivative of chi as a function of the detuning. So apologize for changing notation on you here. This h is just the detuning. All right, so here is a strategy in a nutshell. Guess a good chi and obtain an omega of t. So in our case, we want to do a C0 gate. So we want to use this formalism for that. And here, the challenge is that I have, again, these two blocks. So in the one, now I want with the same pulse again to solve both blocks. But now it's more challenging because I can only solve one block at a time with this chi formalism. So what we did is we just picked a pulse that we imposed it to be resonant with one of the transitions. And of course, a resonant pulse is trivial to solve. You just integrate it. So the non-trivial part remained in this block that had the detuning. So for that block, we used this formalism. And by imposing that our evolution operator at the end of the pulse looks like a generalized C0, so we allowed ourselves some local Z gates here, we imposed constraints on chi. So all you need is guess a function chi of time that satisfies these constraints, and you want the pulse area here to be pi, so you do a C0. And we picked a function that looks like this. This is just one guess. You can sit and guess pulses all day, but this satisfies the boundary conditions, and moreover, you see it has a pretty nice shape. So if you show this to an experimentalist, and we've done that, it's not scary. And actually, there are now experiments on this. So if you now take your pulse, put it in your full Hilbert space, and ask yourself how good is your designed gate, you see that you get pretty good numbers. And this was all the results from 2015, since we've gotten much better. So this is work that our joint postdoc Shuhao Dang did. So we had just done this as a proof of principle. We picked typical parameters for the spectrum and just showed this works. What he did is he went in and he scanned the frequency of both qubits, and he asked how good can the fidelities get. Okay, this is a lot of numerics he did. And he showed that you can have these dark red is high fidelities. So there's big areas of high fidelities. You have some dips where you cross the cavity as expected. And the gate times can still be pretty good. So if you take here cuts across fidelity and time, you see that in general, you have this unfortunate thing where the fidelity drops, here. The fidelity drops when the gate time also drops, right? So you want the gate time to be fast, and you want the fidelity to be high. But you can find, because this drops slower, you can find good regimes where you have fast gate and high fidelity. So he also did more work. Talking with experimentalists, one question came up was, how stringent is this pulse shape? Can I start distorting it and still get something decent? So he added a Gaussian admixture, and you can see here that it's pretty robust. We don't understand exactly why you have this big plateau here, but the fidelity remains pretty good as you deform the pulse. And then he also put in T1, T2 processes and showed that this still performs well. That's not surprising, of course, because you're only at 30 nanoseconds. All right, so more recently, this is not published yet, what we found is that now if we allow any local gates to accompany our C0 pulse, then we can do much, much better. So you see, you can go from a fidelity that's in the order of 993 to 4 nines. And something we see systematically is that the fidelity tends to saturate at the purity, which is something we don't quite understand, but we know that because of this result, we know that we're now limited by leakage. And one idea we are thinking about is combining this well-known drag pulse from superconducting qubits, the drag technique, with Swift. So this is a way to combat leakage. And we want to build into our chi formalism drag. Okay, how much? 5? Okay, so I'll go over this fast. We also worked on 3-qubit gates. The motivation was the fact that Toffoli gates are very prevalent in quantum information algorithms, but they take many pulses, many gates to be decomposed. This is not the optimal decomposition, but you cannot do better than 5 C0s. So we wanted to ask, can we use our ideas to do things like a Toffoli gate? So here we have 3 qubits coupled with a cavity, through a cavity, and we want to implement the CCZ gate. And the way we did this, we realized is the only way you can do it if you want to readily take the Swift ideas and use them here, you do need to do some spectrum engineering. So this is not necessarily the only solution, but it's a solution. So if you hit certain resonances, then you can activate a spectrum that has 2 competing transitions, one target and one harmful, and not the 4 you would expect by just counting how many states do the other 2-qubit have. So I'm going to go through this a little bit quickly, but I'll just flash the result. So what we showed is that you can use a Sedge pulse here to have, in less than 300 nanoseconds, which is more characteristic of 2-qubit gate type speed, you can have a 3-qubit gate, and it performs pretty well. We can already get a fidelity of 995 without doing any optimization. And then if you do optimal control on top of that, you can get something. It looks pretty nasty, this green one, but you can shoot a fidelity to 4 nines. And then this was work done collaboratively with Christian Arendts, who's also here. What he did was they just smoothen out this optimal control solution, and we could still improve the fidelity that way. And another interesting thing he found was that if you just start from a random guess, you can never get the fidelity as good as this. And actually, the fidelity was worse than what raw fidelity we're getting without optimization. So I think this is an argument as to why this sort of hand-in-hand analytical plus numerical is a good idea. All right, so now this takes me to the experimental implementations. There's an experiment using the Sedge pulses that our colleague, collaborator Dave did at NIST. There's another recent experiment where they used the work of Dave's and our ideas to do an entangling map gate, and there's 2 unpublished, so I cannot show you data since these are unpublished, but one was, they were both presented at March meeting this year using the 2-qubit gate. So I'm gonna flash these quickly. So here, this was theory, and this is experiment by the NIST group. This is on a transmon. This is a single transmon, single qubit gate. So you can see here the behavior of the Sedge as you expect. The Gaussian behaves differently, and the square pulse behaves as I showed you before. And you can get pretty high phase gates, single qubit phase gates, high fidelity using this technique. So here you have the average fidelity as a function of the detuning. This asymmetry here is not surprising, because if you detune the one way, you go away from the transmon ladder. If you detune the other way, you hit these excited states and you start leaking out. And the problem we're now dealing with is, okay, we designed a nice 2-qubit gate. It's very fast. But we have to go and revisit the question of what about single qubit gates, right? I told you in the beginning that an inherent challenge in these always coupled, no tuning systems is that you have to do both, single and 2-qubit gates with whatever spectrum you're given. So here you have the opposite problem that you had before. You have 2 different 2-level systems, subspaces, and now you want to do the same gate on both, even though your Hamiltonians look different. Before we want to do very different gates on each. We have a technique of doing that. Now I want to do the same thing on both. So to achieve that, you could either think of doing broadband pulses. So if this delta is not too large, then maybe you can have a broadband enough pulse that covers both transitions. Or you need to do something smarter in terms of pulse shaping. We're exploring both. So if you look at broadband pulses, we have examples of a bunch of gates that work. So one example is a rotation, pi/8 rotation about the x-axis using a broadband Gaussian. And you can get OK fidelities for single qubits, 994. And then to do pi/4, we realized that just increasing here, the pulse area did not work well. So we combined two of these with some phase. And we found the peculiar result that if you square this thing, you get something obviously less than this. So combining two of these pulses is better than just doing one. And the reason is somehow the second pulse must be compensating for leakage. So this also points to how complicated this transmon system is. It's, and other people have seen similar things when they were simulating cross-resonance gates. All right. Finally, I'll just want to point out another challenge we're facing in these systems. This is related to the fact that these two states have different frequencies. So now a gate you design at some certain time, if you want to repeat this gate at some later time, you're going to have picked up a different phase here. So this is a challenge. One way is to just clock your system, so you always do gates in 2 pi over epsilon. The experimentals are not too crazy about this, so we're working on doing gates with arbitrary phases. But this sort of points to how challenging it is to do quantum computing with this type of third paradigm. Finally, I just want to advertise this other approach of dealing with the single qubit gate question. So this is based on work by my colleague Ed, who's here, and some of our postdocs. Here you have a Hamiltonian that has some error in this off diagonal. Ideally, this is 0. And you want to do a gate that doesn't care about this delta H. So they've come up with a way of making robust gates that are to some order in delta H work well. And this we could use to do single qubit gates, because if these shifts are small enough, then you can deal with them. So they have some error cancellation conditions coming from the evolution operator in the Schrödinger equation. I'm not going to go too much into this. All I want to show you is that they have a very cool way of doing pulses that are robust to these fluctuations. And they do it by just drawing curves in a 2-dimensional space and then reading off what the pulse is through the curvature of these curves. And the conditions here are that the curve, if the curve goes back to itself, then you cancel first order error. If the curve is a closed loop with 0 area, so this area compensates for this, then you cancel second order error. So this is an interesting result. It was motivated by nuclear noise in quantum dots. But you can use it to do things like control when the two systems are not identical, and we're exploring this. All right, so to summarize, I discussed how we propose to do 2-qubit gates, single qubit gates, and also 3-qubit gates in superconducting transmon systems. What's more interesting to me is where the future is. So in these systems, understanding the spectrum, as I said, it might sound like a boring thing, but it's very important in designing gates, and you have a vast number of parameters. The other thing is that the community, especially experimentals, have been working to optimize coherence, but sometimes just getting the best coherence possible does not solve your problem because you make control difficult. So living somewhere in between where your coherence times are good enough but your controls are also fast is more important, so we're thinking about that. Then another, in the same lines, optimize single and 2-qubit gates at the same footing. Don't try to make the best single qubit gate ever, and then your 2-qubit gate will be hard, or vice versa. And of course, you have to worry about what's finally your architecture in your quantum information processor, right? You can fit that many qubits in a cavity. there's a finite number you can fit. So how much can we get out of always coupled systems? I think this is an open question. How scalable is this approach? Ball shaping can take you this somewhat far, but cannot address this cannot fit an infinite number of qubits in a cavity. And I think it's interesting for the community to reconsider some paradigms. So one thing is making the frequency of the resonator higher than the qubits. That was done for coherence purposes, but it does complicate control. So I think revisiting this issue now that coherence times are going up is important. I want to acknowledge my collaborators in this work. Other people have also worked on this, but these are the most important contributions. And finally, I just want to flash that we're doing more things at Virginia Tech, and we have open postdoctoral positions. So please, if you're interested, or if you know people who are interested looking for a postdoc, one of these positions is at the more senior level, coming with more responsibility and higher salary. So if you know anybody that's interested, please contact us. Thank you.
Thank you very much. So I see that there is already one question.
Thank you, Sophia. That was a beautiful talk. It struck me during the first part of the talk that many of the problems you were describing map actually in an analogous way to the ideas of spin-motional disentanglement in trapped ion systems. And I was wondering if you had either looked at the solutions that that community has come up with for loop closing techniques using pulse shaping and phase modulation techniques like we had thought about, or if you've looked at how the Swift or Swift-like approaches map over to these bosonic mode decoupling problems.
So I haven't thought about it in too much detail. I've talked a little bit, at some point Jun Sang visited us and we talked a little bit about it. I think the Swift is very general, so maybe say that first. Right? So long as you have one competing transition at your main transition, you can do that. You can do Swift. So Swift can sort of span over all these paradigms that I discussed. I think in the case of trapped ions, you can do. The difficulty is that for me, it's not a system that I'm very familiar with, so I'm very interested in discussing more, and I think this conference is an excellent opportunity.
I've glimpsed another question. Yeah. We have plenty of questions located there. It's good for me.
Thank you. So thanks for the nice talk. I have lots of questions, but one, have you thought about seeing whether there are some optimality conditions that either the SETCH or even better, the new solution you're after, they might obey in terms of like, I would like to say time bandwidth constraints, but this is because this relates to things I am looking at. Could be even variational or could be something like that, and then see whether you get equation that can probably tell you what the analytical solution is optimally.
So you're talking about time optimal, yes?
No, both, because you have this competing effect between the time and also the bandwidth.
Right, so in terms of time, in the formalism, the Sky formalism, quantum speed limit is built in. So you know where the quantum speed limit is. That's
yes,
one
sure.
Point. In terms of bandwidth, we have not done that. So that's something that we could do starting from this, knowing where the quantum speed limit is and going toward bandwidth.
Or let me rephrase the question. For the SETCH, which is a well-known old solution, do you understand why that behavior is the way it is? So analytically, why it keeps phase,
so
it closes the...
It does have to do with the non-adiabaticity. It does not map to adiabatic, but I don't have a better answer. That's something I've asked my students to look into, but we have not done yet.
Mm-hmm. So Klaus, you had a question.
I had a question to the Dave Papa experiment. That you showed. So you showed a bandwidth just around 0 detuning. Is that very, very long pulses, or did I misunderstand if there's an offset in that figure? I mean, you get this wonderful gate, and if the detuning is close to 0, how can you get a very high fidelity?
So detuning means detuning from the transition you're driving.
Okay, so it's not the detuning between the two frequencies?
No, because in this case, I should emphasize this is single qubit. Okay. So far, he's only done a single qubit as a warm-up toward two qubit, but not Actually, another group, I should probably acknowledge other people's work. This paper, they have used the such as a helpful handle in their 2-qubit gate. But we have not, our collaborators have not done that.
Okay, so last question, because we have to...
It's short. The work you showed from your postdoc where you screened, excuse me, the parameters, did you, or did he or she, at the end do optimal control
Yes.
as well?
No, okay, so we have not done optimal control, but he did tweak parameters. So one thing is that inside our analytical recipe, there's a parameter you change. Every time you move around here, there's a parameter you know how to change analytically. And then on top of that, he did just a little bit of search. But we have not
on
done
the shape,
OCT. And actually,
on the pulse shape.
on pulse parameters, yes, pulse parameters, not the pulse shape per se. But the optimal control is something we're very interested in doing. We've done a little bit of it, but we rather collaborate with experts on that rather than reinventing the wheel.
Okay, so I think it's time to thank Sophia again.